So I thought what I'd do is give just a little bit of background for those that aren't as familiar with that, a little bit of maybe some learning that you can leave with on what is artificial intelligence, machine learning, deep learning. Use your favorite buzzword there. It's all basically and relatively the same with minor subtle differences. And then after that, go in a little bit more about the architecture we utilized at SparkCognition to solve Jason and Invenergy's use case and problem. So machine learning is everywhere, whether it's Facebook being the obvious one. I don't know if you guys know, but when you hit the like button, tons of machine learning there with its only goal to get the right advertisements in front of your face based on your preferences, based on what you like, et cetera, et cetera. Especially here in California, self-driving cars with Google, very popular. IBM Watson, you guys have probably seen the Bob Dylan commercials where Watson can write a song, and I guess now it can apparently start doing your taxes with TurboTax or whatever their new, or H&R Block, I think. So these are all very powerful machine learning or artificial intelligence engines that are being utilized out in the market today. So a little bit of a primer. Let's first talk about, when we talk about machine learning, let's talk about unsupervised learning. So let's assume that this picture here, and let me just move forward one, is a bag of marbles that you've collected. All right, so in an unsupervised case, we want to bucket the marbles in some fashion. Well, how would we do that? Well, what we have to do in the machine learning world is look at things called features. So features could be colors, features could be the size, features could be the pattern. The nice thing in the artificial intelligence world, as opposed to maybe how subject matter experts have approached the problems before with, they've been doing things for 20 years, they have biases. Machines aren't biased. So we can look at ridiculous features like maybe color divided by shape or shape times patterns, and we can extend the sort of the nominal feature space to second, third, and fourth order features. That allows us to look at a lot more correlations that may not have previously been obvious. So in this case, we train the system and we look at features, and using artificial intelligence techniques, we let the computer understand what the best feature is to bucket these marbles. So in this case, if this animates right, it picked that the best way to animate or to decide what was the best way to classify these marbles is based on whether they were small, medium, or large. Okay, that's an unsupervised approach. Now, if we talk about supervised learning, now what happens is you're actually given the buckets. So we know that the buckets are red, green, and blue, and now we train the system on what does a red marble look like? What does a blue marble look like? What does a green marble look like? And now we can actually classify that because we give it pictures or examples, for lack of a better word, of what a red marble looks like, et cetera, et cetera. This is very similar to how, like for instance, voice recognition works. It was basically trained on thousands of words, thousands of sentences, many different dialogues to basically train and understand patterns in speech and recognition in speech. So, let it animate, it goes to red, green, and blue. Now, many of you and your plants aren't dealing with a bag of marbles, so let me try and hopefully equate it to something that you might be used to, which is an Excel spreadsheet. All right, so here's an Excel spreadsheet of operations at a plant where you've got maybe a particular wind turbine, you've got the date, you've got the time, what its ID is, and some value. Let's say for this conversation it's temperature. So now when we take a unsupervised approach, we look at temperature, maybe there's some vibration data, maybe there's some pressure data, and we look at correlations in the data. And essentially what we're looking for now is anomalies, things in the data that look strange, that don't follow patterns, that aren't within typical operating ranges or procedures. All right, so that's an unsupervised approach. One thing to understand from an unsupervised approach is you can't predict failures in terms of time in an unsupervised method. So if somebody tells you that they can do like a remaining useful life calculations without having examples of what a failure looks like, be leery, let's say, for lack of a better word. So now you bring in the supervised part. Now I know at this index there was a repair taken on a blade. Some action that was unknown was on a blade. We've got some no trouble founds. We've got repairs on gearboxes. Now what you can do is marry and merge the supervised data with the unsupervised data. So you look for those same patterns, those same anomalies, but now you can correlate to that to some failure mode, some failure signature that makes sense to the operators. And that's basically what we did for Invenergy, is we had examples in this use case. We've done other use cases where it's been unsupervised, where we've just looked for anomalies, operational conditions. But in Jason's case, we actually took a supervised approach because we had that some failure information available to us. And we essentially developed what's called a risk index. So as Jason mentioned, we took the pi variables. There are about 30 variables per turbine. We ran, some of our algorithms based on that information, based on some of the historical data, based on some of the failure information. And essentially what it's showing, as Jason mentioned, is this is kind of a unitless thing, but above this line, we were able to, with 70 days advance notice, with about 75 to 80% accuracy, give them a warning that an impending failure is about to occur. When it goes above this line, which if this was colored is kind of our red indicator, we could give with 90 to 95% accuracy that the probability of the gearbox failing is going to happen within the next 35 days. So what does that allow Invenergy to do? It's not that they're necessarily going to go out and immediately fix this thing just because the probability goes above this line. But what it does is when Jason's looking at a fleet, they've got thousands of turbines, remote locations. Some locations might have a couple hundred turbines there. It costs a lot of money to get a crane out there to repair these things, to do the maintenance. There's safety aspects. If they can plan for that, if a crane costs $250,000 to go out to a plant or a wind farm and fix that, that's a big cost. If there's 5 or 6 turbines that they know of are somewhere in this state, well, now it doesn't cost so much. They can amortize some of that maintenance cost across there, as well as reducing the downtime within the system. So that's one of the values of implementing a system like this.